Hello everyone, welcome back to the lecture series on fundamentals of generative AI and large language models. In today's session, I will be discussing about image to image translation using Pix2Pix GAN. Okay. So, we will have a look into the contents, introduction to Pix2Pix GAN, difference between conditional GAN and Pix2Pix, application of Pix2Pix GAN, unit architecture for generator model in Pix2Pix, PatchGAN for discriminator model, weight updation of generator and discriminator in Pix2Pix, and training and inference of Pix2Pix GAN. So, we will start with introduction to Pix2Pix GAN, what exactly it is. So, basically Pix2Pix is a specialized implementation of conditional GAN. So, it itself is a conditional GAN, but it is specialized for image to image translation, and it was introduced in the paper image to image translation with conditional adversarial network in this paper image to image translation with conditional adversarial network by Phillips, Isola and his team from Berkeley AI Research Lab. Okay. So, we will see what is the core idea behind this Pix2Pix GAN. So, basically it is for image to image translation. That means we have one kind of image in the input and some other kind of image as the output. So, here we can see the input is edge, the sketch kind of thing, and photo is the output. Okay. So, this is one kind of image to image translation. Then we have map input and satellite output, that is another one. Then we have a sketch input and the painting output, that is another kind of image translation. Low resolution input to super resolution output. So, this is one more image to image translation, and then we have, this is an image which is damaged. From a damaged image it has been repaired and we have the good image from that damaged image. Okay. So, that reconstruction have been done. So, it is also image to image translation work. Now, Pix2Pix is specialized for these kind of tasks where one image is the input, another image is the output. Now, what is the difference between conditional GANs or CGANs and this Pix2Pix? Pix2Pix basically is a type of conditional GAN. It is a specialized conditional GAN. Now, what is the difference between normal condition from the conditional GAN? Why it is specialized? Where exactly is the difference? We will try to see that one. So, conditional GAN is a generic conditional generation framework. Okay. So, it is very generic, can use labels, text, images, etc. as the condition. So, it is a generalized framework, whereas Pix2Pix is a specific type of conditional GAN which is specifically designed for paired image to image translation. Okay. So, this Pix2Pix has little bit of certain changes in the architecture which helps it for a image to image translation task. Okay. Now, when the paper came out, the original paper of Pix2Pix, there were lot of artists and other people from the artist background or graphic practitioners, visual artists, they used Pix2Pix in a various ways. So, these are few of the images. The image has been taken from the original paper. So, it has been used for various applications by online community. So, it is from a sketch to say an image, and then background removal. You can see here the picture is having a background, here no background, then the sketch to Pokemon, then palette generation. If you see, this portion is black, where here that portion is having some colors, and then there is do as I do as I do. So, do as I do is basically a pose transfer. So, that pose is transferred to the output image, and then sketch to portrait, then photo generator. So many various kinds of applications of this Pix2Pix GAN have been lot of visual artists and graphic practitioners, they have used for various kind of these applications. Okay. So, there is a huge range of things that can be done using the Pix2Pix. Now, what is the architectural difference between conditional GAN and Pix2Pix? Let us have a look. So, this is the picture which we all know, and picture of conditional GAN, and this is the picture for Pix2Pix architecture. If you see, the main difference, everywhere it is same. The main difference is in the generator, here we had a neural network, where here it is an unit. So, a unit is used as the generator in case of Pix2Pix, and here the discriminator in conditional GAN was also a neural network. In this case, it is a PatchGAN. So, we will come to what a PatchGAN is a little later, but for time being we will know that in Pix2Pix the generator is made up of a unit architecture and the discriminator is made up of PatchGAN. So, that is the main difference, architectural difference between conditional GAN and Pix2Pix. Okay. So, these are the two things that we have to concentrate on. We will have a look. So, we all know what a unit architecture looks like and what is the use of unit architecture. Till now we have seen that unit is used for semantic segmentation, but now we will see how it can be used for the generator in a Pix2Pix. So, if we see, this is a very known picture of unit, and then we have this downsampling and then bottleneck, then there is the up convolutions. So, this is basically the encoder path, which there are operations like convolution, 3x3 convolution, ReLU. So, these are convolution and ReLU. Then we have max pooling in these red arrows which shows, and these blue arrows shows a 3x3 convolution and ReLU, and there is a spatial dimension decrease with each level of max pooling, and this is this portion where the spatial dimensions are coming down, we call it as an encoder path, and where the spatial, here it is up convolutions, this portion is called as the decoder path or the expanding path. So, encoder and decoder we have. Then we have the bottleneck, which is this portion, and it has the compressed information, the important information in the most compressed way. Okay. So, in this case the unit architecture just takes the input image, suppose this is a sketch, and the output image, or it generates an image with the like a photo. Okay. So, the unit is basically trained for filling up, which are the places which should be filled with color, what kind of color for what kind of structure. So, all these are trained in the unit during the training time. Okay. And the encoder basically extract the features from this sketch. So, all the fine details, the edges, the lines, the everything, the finer details are extracted using the encoder, and then the bottleneck compresses all the informations and give all the important information in the most compressed form, and the decoder reconstruct the images. Basically, it generates the image, it generates the photo or the painting that we want to get out of the generator of the Pix2Pix. Now, these are the skip connections, which is a very important part, and this is the reason we do not use normal encoder decoder architecture. We Pix2Pix uses this unit architecture because of the presence of the skip connections in unit. So, what happens is skip connection helps to preserve the low level spatial details lost during the encoding. So, as we know, during the encoding, as there is a decrease in the spatial dimension, what happens is a lot of finer details start getting lost. So, that those information which was lost because of the skip connection between the encoder and the decoder, those lost informations are again retrieved back and placed here using the copy and crop and crop copy, and then they go from the encoder to the decoder. Okay, so this skip connection is very important for Pix2Pix, because otherwise the photo that is generated, or the generated output image, in this case this photo from this sketch, they will lose the finer details. Okay. Now that is about the unit that is used as the generator in Pix2Pix. Now what about the discriminator in Pix2Pix? We have seen that PatchGAN is used as a discriminator in Pix2Pix. What is this PatchGAN? It's a type of discriminator that classifies whether each n cross n patch is real or fake. That means previously we have seen in conditional GAN that the discriminator sees the entire image and then tells whether it is real or fake. In this case what happens is, if you have 256 by 256 one image, then it will patch by patch, the discriminator will see whether that patch is real or fake. So, let us have a look. So, suppose this is my real image and this is my generated image. Okay. So, you can see the real image is having much better resolution, the generated image is very blurry, but it is capturing some of the details of the the real image, but it is very blurry, the resolution is bad. Now in PatchGAN what happens is, this patch the discriminator will see, and then it will see whether this portion is exactly matching with this, is it real or fake, then another patch, then another patch, another patch, another patch. So you have patch by patch, n cross n sized patch by patch, the discriminator will see, and it will tell whether it is a real image, or that patch resembles the real image completely, or it looks like a fake image. Okay. So that is the main idea of PatchGAN, and the final discriminator output is the average of all the patch decisions. So every patch there will be a decision, right. So whether it is real or fake, real or fake, real or fake, and the overall decision of the discriminator is the average of all these patch decisions. Now the next question comes, how big should be the patch? What is the ideal size of the patch? Okay. So let us see that one, what is the answer to that. So in the original paper, experiments have been done with various patch sizes. So people have, or the scientists working on that paper, they have done experiments. For 1 cross 1 patch size, you can see the color correctness was there, but there was no effect on the spatial statistics. So you can see it is not a very clear thing. The color is correct, the color has been captured correctly, but spatial statistics or spatial information is not that clear in this 1 cross 1 patch. In 16 cross 16, we see there are locally sharp results. So it is not as blurry as 1 cross 1, but creates tiling artifacts. If we see these, there are some artifacts here. So there is artifacts which comes for the 16 cross 16 patch size. Then scientists have tried 70 cross 70. This is having sharp output, even if incorrect in spatial as well as spectral dimension, means it is having sharp output. Some of the places the spectral and the spatial information is not exactly correct. And then they tried with 286 by 286 size. It is, the output is visually similar to 70 cross 70 PatchGAN, but the matrix gives lower score. So from the paper, it is decided that 70 cross 70 PatchGAN gave the best visual representation with the matrix, performance matrix FCN is it's good. So because 286 cross 286, this metric went down, FCN metric score value, it went down. So this is the best trade off for the PatchGAN discriminator, 70 cross 70 patch size. Okay. Now, we will have a look how the training of the Pix2Pix GAN happens. Suppose I have a sketch of a scenery and I want a painting of the same sketch, which is my target image. So, the sketch of the scenery is A and the painting is sketch B. Okay. So, this is my scenery, this is the sketch, this we call as real A, and this is the target, which is the painting, and this is my real B. Okay. So, real A and real B. Now, we will look into how the training happens in the architecture. So, we have the generator, basically it is a unit model, and then the discriminator, which is the PatchGAN, we have already discussed about it. Then the real image and the real A and real B plus. So, both of them go to the PatchGAN, both goes to the discriminator. Okay. So, the discriminator's input is real A as well as real B, whereas the generator takes real A as the input. Okay. Now, it generates a fake B. So, it generates some image. If you can see the resolution, it generates something, but it is not as same resolution as real B. So, this is a fake B, and then it adds this real A, and both of these things go to the discriminator. Okay. So, the discriminator gets real A, real B, fake B as well as the real A. Okay. So, it has information of all the things here. Then the discriminator sees whether it is real or decides whether it is real or fake. As we know, this discriminator gives a probability score whether it is real or fake, and depending on the correctness of the answer, there is discriminator loss and generator loss. These are back propagated. The discriminator loss gets back propagated to the discriminator, and fine tuning happens on the process of training the discriminator, whereas generator loss gets back propagated to the generator, and through iterations of training the generator becomes more and more efficient in making fake images look very similar to real images. Okay. So, this is what happens in the architecture of Pix2Pix, and this loss is basically the GAN loss or the binary cross entropy loss. We will look into details what exactly it is in the subsequent these ones in the next slides. Okay. Now, we will have a look how the weight updation happens in the generator during the training. We know, as I was telling, in each and every iteration the generator becomes better and better in its performance, that it starts generating images, fake images, which looks very similar to the real image. Okay. Now, for doing this one, there should be some weight updation that is required in the generator. That is how the performance can be improved. Okay. Now, we will see how the weight updation happens in the generator. So, we know the generator is a unit, and the input image to the generator is the sketch, which is your real sketch, and it outputs some fake B. Okay. Outputs some generated image of a painting. Now, and this is your target image, which is the actual painting, okay, which is your real B. Now, what happens is, whatever is taken out of the generator, or whatever is generated by the generator, and whatever is the target image, these two are processed through mean absolute error loss. So, what exactly it means? It means that this mean absolute error, it takes out the difference between the actual target and the generated target. Okay. So, pixel by pixel, how much it is varying, that is captured by the mean absolute error loss, which we call as the L1 error loss. Now, so this is one part of the error. Now, this generated image by the generator goes to the discriminator, and all labels are 1. I will come to this one, I will explain a little later. We will first see the entire process, and then I will come to why I have written this all labels are 1. Okay. So, once the generated image goes to the discriminator, then the discriminator also gets the target image here. Okay. So, it goes to the target image goes to the discriminator also, and then what happens is during training the discriminator gets the real target image as well, and then it is able to distinguish between whether the generated image looks similar to the actual target image. So, it will find out the binary cross entropy loss between the generated image and the target image. And here we have seen that we have taken a mean absolute error loss. What was that absolute error loss? Between pixel by pixel, there was the difference between the generated image and the target image. Now, that mean absolute error gets multiplied by a factor lambda, which is in the original paper they have taken it as 100. We will come to that later. I will speak a little more about lambda, why 100 they have taken, and this lambda into the mean absolute error loss and the binary cross entropy loss, these two are added together and we get whatever we get as the total loss, that is passed through the gradient descent. So, the gradients are applied and the gradient descent happens. The loss, for minimizing the loss, it goes back to the generator, again the generator's weight updation happens and the training process continues. Okay. So, this is the overall how the weight updation happens in generator, what exactly happens in each and every phase. We had a look, and now I am coming to all labels are 1. So, what exactly I mean by this statement? See, during the generator's training, fake images are passed through the discriminator. We have seen this is the fake image. So, this is my fake image, correct. Now, this fake image is passed through the discriminator. Now, the generator wants the discriminator to predict this one as 1. This is D, as we all know, this is the discriminator's score, probability score for this real image and the generated image, and the generator wants it to be 1 because it wants to fool the discriminator. So, it is labeling all the fake images as 1. So, the binary cross entropy compares fake outputs against the label 1. So, it is label 1 is there and the fake images are there, and then the binary cross entropy happens here. Okay. So, that is the reason all labels are 1. I have kept it here. Okay. So, the total generator loss is the binary cross entropy loss plus lambda L1 loss. Okay. Now, this lambda value has been taken as 100 here to give more importance to pixel by pixel difference between the fake image and the actual target image. Now, we will see what is the generator loss in Pix2Pix GAN. So, we will have the mathematical things here. So, total loss is the CGAN loss, conditional GAN loss plus lambda into L1 loss. Now, this CGAN loss is basically the adversarial loss or the conditioned GAN loss, we all know that one. Just to give to make the mathematical expressions a little more easy to understand, I have put the real image, original image as X here, and real target image as Y here, and the generated target image as Gx. So, it is generated by the generator, what it is trying to generate is X. Okay. Now, what is the mathematical form for the CGAN loss or the conditional GAN loss? Conditional GAN loss is written as the expectation value of x comma y log dxy plus expectation value x comma y log 1 minus discriminators x and gx. So, what exactly they are? We all know this is the probability score given by the discriminator for the real image and real pair of images, the original and the target image, whereas this is the real image and the generated target image. Okay. and if you see this is the CGAN loss, and the L1 loss is basically it is the difference between your actual target and the target that is made or generated using the generator. So, it is an absolute difference between them. So, it is the L1 loss, and this ensures that the generated image is pixel wise close to the target. So, pixel by pixel there will be comparison, and this loss ensures that if when this loss is minimized, that means each and every pixel of the generated image is coming closer to the pixel of the target image, okay, each and every pixel. Now, in the original paper lambda is equal to 100 they have taken, and this is used to strongly emphasize L1 reconstruction loss. That means more importance is given for this pixel wise comparison and reduction in the error. Okay. Okay. So, this gives a strong weight to pixel similarity. Okay. So, that is what is measured in the L1 loss. Now, these are some results from the original paper demonstrating the output quality for various type of losses. There may be a question why we have taken lambda this L1 loss, why it is not only the conditional GAN loss, why it is not only the L1 loss, but why it is a combination of both. So, the scientists working on that paper, they have done experiments with, so these are the input images, these are the ground truths. This is with only L1 loss, this is only with conditional GAN loss, and this is L1 plus conditional GAN loss. So, if we see for with L1 the outputs are not that great, only with conditional also there is improvement, but if we see the combination of L1 plus CGAN, it is much better. So, that is the reason L1 lambda into L1 plus conditional GAN's loss is the loss that is taken for this architecture. Now, weight updation in discriminator, we will see what exactly happens here. So, we have the discriminator which is basically the PatchGAN. So, we have the PatchGAN here, okay, and the PatchGAN gets the target image, and PatchGAN gets the input image also, and the input image goes to the generator also. So, discriminator gets target as well as the input image, the generator gets only the input image, and if you see the generator generates the fake image here, okay, and this goes to the discriminator. Now, the discriminator will calculate two losses. One is called as the real loss, which is given by minus expectation value over xy log d of xy. Why it is real loss? Because we are taking the real image and real original image and real target image, okay. And there is it is a sigmoid cross entropy between all ones and the real images. Why? Because here it is the discriminator will be giving or tagging all the real images, the original and the target images, they will be tagged as 1 because they are real, okay. So, the loss will be calculated between all ones and the real images, and here we have the generator loss, which is basically sigmoid cross entropy between all zeros and fake images, because the generator will tag every generated image as 0, and so the loss is basically the sigmoid cross entropy loss between all zeros and fake images, okay. So, this is expression for fake loss, and this is the real loss, sorry, not fake loss, generated loss, and this is the real loss, and then these two are added together and we get whatever is the total loss, the gradient is applied, and then gradients are up, because of the gradients the weight updation happens in the weight updation happens in the discriminator, okay. So, this is how the discriminator gets trained, and total discriminator loss is L real plus this one, which we can call as the generated loss also. Now, we will have a look into the training details, what exactly are the parameters. So, during the training of this Pix2Pix, one gradient descent step in discriminator is done and then that is fixed, and then the generator training is done. So, it is done discriminator, then discriminator's weight adaptations happen, it is kept constant, then the generator's weight adaptation happens. After that, once again it goes iterative way, discriminator happens, generator is that time it is kept constant, and once the discriminator is trained, that is kept constant, generator's weight adaptation happens. So, this happens in an iterative way. The optimizer that is used in the paper is an Adams solver, and the learning rate is 0.0002 with beta 1 and beta 2 values of 0.5 and 0.999. Okay, so these are the parameters of the during the training process that is used. And a very important thing which I would like to mention, during the inference discriminator is not used, because the role of the discriminator is to push the generator to improve its performance to a level where the generator can generate images which exactly matches with the real image or very similar to the real image. Okay. So, during the training time both the generator and discriminator will be there, but during the inference time discriminator is not used. It is only the generator with all the learned parameters that only works, and it generates the images, fake images, and batch size is usually during the inference it is 1 to 10. Okay. Now, objective function of Pix2Pix. What is the objective function? We know that cycle GAN, conditional GANs, we have this is the loss, okay, and the objective function is given by G star equal to argmin G max D L conditional GAN plus lambda L1 GAN. Lambda L1. So, this is what exactly it means. Argmin G means the generator tries to minimize the objective function, and max D means the discriminator D tries to maximize the objective function, and this is my L1 loss multiplied by lambda. Okay. So, this is the objective function of the Pix2Pix. And with this one I come to the end of my session today. Before I conclude fully, let me summarize little bit about what we have learned today. So, we have studied Pix2Pix GAN, which is a specialized conditional GAN framework which is specifically used for image to image translation. So, the main difference between a normal conditional GAN, which is a generalized version, it can take the conditions from images, text or any other modalities, but here in this case the main difference of architecture between the standard conditional GAN and Pix2Pix is that the generator used is a unit architecture and the discriminator is a PatchGAN, and that helps in the image to image translation. Okay. So, we have seen that architectural difference, then we have seen how the weight updations happen in the generator and the discriminator, what are the different kind of losses that are coming into picture during weight updation in the generator and discriminator, and finally we have had a look into what is the objective function of the Pix2Pix GAN looks like. And so, with that one we come to the end of today's session. In my next session I will be discussing about cycle GAN, that is another variant of GANs. Till that time, happy learning. Thank you all.